Okay. Hopefully I will be able to get through this without having to blow my nose. Um, Today we are working on recurrence relations. So, although I may be jumping the gun a little, recurrence relations are like recursive functions. You got like your function and then your function call inside the function with your base case somewhere. The cool thing about that is that it works in the math too. So first we want to talk about sequences though. Sequences are just ordered lists of numbers. And sometimes we feel like indexing from 0, sometimes we feel like indexing from 1. It won't really matter. If you're paying attention, it will just probably, like, you won't have to come up with it on your own. Like, you're probably going to be told what you're dealing with. So for example, in the sequence 1, sequences are usually indexed by I, so the ith component would be a to the I. A equals sequence, a to the I equals the I space. So in the sequence 1, 2, 3, 4, assuming that a to the 0 equals 1, right now we're indexing from 0. I think that indexing from 1 is more common, so that's a good thing to keep in mind. But since we're indexing from 0 here, a3 is going to be 4. Okay? Next on the chopping block, right, so these sequences are usually notated as a to the n, or a of n, I don't know. I don't want to say a superscript n, so it's not particularly clear exactly what to call it, because they just write brackets a to the n in the book, and I'm like, well, what am I supposed to call that? But we make do. So it's very common in these types of sequences to have the index be part of the equation. So for example, a n is going to be one over n for n greater than 0. So that sequence looks something like 1, 1/2, 1/3, 1/4, etc. They really emphasize this geometric and arithmetic progressions, so I'm going to show them to you. Even though they show up, I haven't seen how they're relevant yet. So that's really important to keep in mind, because they will very commonly point out a sequence that shows up in this form as geometric progression, and sequences that show up in this form to be arithmetic progression, where c is some constant and d is also some constant. Oh, I put in a random r. I put both of these as r. I think that these are, no, that one is r. That one is d. I don't know why it's the d. It's just a number. C, just a number. C, just a number. It doesn't super matter. C is the initial term. C is the initial term. D is just the proportion. You got all this. This makes sense. It's just a little confusing, but most important about both of these is that C is the initial term, and N is the index. It's pretty common that sequences like this are used in computer science. I mean, anytime you use a for loop, you're probably, especially in Python where for I in range, super common. Range is just a sequence from 0 to n minus 1, so okay. Now that we've got the boilerplate out of the way, we can go on to recurrence relations. Sometimes we want to define a sequence in relation to previous members of the sequence. So for example, a of n is equal to a of n minus 1 minus a of n minus 2 for a of 0 is going to be, what do we want a of 0 to be? Let's have a of 0 be 3 and a of 1 be 5. So how does this look? Well, we have a of 0 and a of 1, so what's a of 2? Well, we look back and we say a of n minus 1 is going to be a of 1, which is 5, and a of n minus 2 is going to be a of 0, which is 3, so 5 minus 3 is going to be 2. So now we have a of 2 is equal to 2. So we go back, and a of 3 is going to be equal to a of n minus 1, which is 2, minus a of n minus 2, which is 5, and that's going to be negative 3. So a of 3 is equal to negative 3. And we can continue. We will not continue. So that's what recurrence relations are. They just take previous members and use them as part of the formula. So relative to the index. And it's really important, they have to have base cases. And not only that, they have to have enough base cases to fulfill the main case. Because if you just have a of n minus 1, because if you're trying to get a of 1, you can't. So you have to have an a of 1, because you can't, if you don't have an a of 1, then when you try to get a of 1, you get a of n minus 2, and then you're at negative 1, and then it's just terrible. So you have to have enough base cases to fulfill the stuff. So the Fibonacci sequence is a pretty popular example of this. It's just f of n is equal to f of n minus 1 plus f of n minus 2. You could probably have figured out, because you know that it's 1, 1, 2, 3, 5, 8, 13. I'm not going to try anymore. But how do we show that? So the one thing you might not realize is that even though we look at it and we say 1, 1, 2, 3, 5, 8, 13, f of 0 is 0, and f of 1 is 1. Because otherwise it doesn't work. Like usually we just look at this empty space and call it 0, but we don't include it in the sequence. But it is part of the sequence. It is just ill-considered. Most functions can be represented as recurrence relations. For example, a of n is equal to n factorial. We can turn this into a recurrence relation, first off we have to look at n factorial, and well, what is n factorial? Well, it's n times n minus 1 times n minus 2 times dot dot dot, don't forget our parentheses, times 1, right? So if we just cut off n right here, right, we see that this is just, it's just n times n minus 1 factorial, right, because that's how factorials work, which means that a of n can really just be n times a of n minus 1. We don't even have to get a factorial there, because a of n minus 1 is already n factorial, or n minus 1 factorial. We just don't have to say the quiet part out loud. So that's nice. And this is called a recurrence relation, but a of n equals n factorial is called the closed formula to this recurrence relation. And now, give me a quick moment while I blow my nose. Hopefully, I effectively muted my mic. If not, you got to listen to me blow my nose. If so, you were stuck in silence, alone with your thoughts for maybe too long. But that's okay. So, to clarify, a closed formula is defined as it just represents the sequence without recurrence. So you don't see a of n in any form in the formula, or a of whatever. So now just a few practice problems. A of n equals a of n minus 1 plus 3. A of 1 equals 2. So if we remember in our arithmetic regressions, arithmetic regressions look like a of n equals c plus d of n, right? At least in a closed form. So that's important to remember. I don't know if we're actually going to wind up using that, but that's okay. So I mean, if we just look at this, we can probably turn it into its arithmetic form just by knowing a of n equals, we know the initial condition, which is 2 plus d of n. The thing is, if we just do some thinking, a of n equals n minus 1 plus 3, right? So at a of 1, it's just going to be 2. At a of 2, it's going to be 3 plus 2, which is 5. And it'll go 8, and then it'll go 11. So it can't be 3n, because at a of 1, it would be 5 already. And that's too fast, because a of 1 is 2. So n minus 1. And now we have a formula that fits with this. Because we know that this goes 5, 8, 11, 14, etc. So if we plug, let's say, what's 14? 14 is 2, 3, 4, 5 in, so a of 5 is equal to 2 plus 3 times 5 minus 1, or 2 plus 15 minus 3, or 2 plus 12, or 14. Yay! So another way to do this is, well, there's a couple. So I like using the form of the arithmetic regression. I really only just figured that out as an option. That wasn't in my slide notes, so I would take it with a grain of salt. Consider instead, well, I want to keep the formula on the page. So a of n equals a of n minus 1 plus 3. First approach is just sort of looking at, which is sort of what they were having us do, right? It's sort of looking at the change in n, right? Like a of 1 is equal to 2, right? And a of 2 is equal to a of 1 plus 3. And a of 3 is equal to a of 2 plus 3. So what are we noticing? That these are all just going up linear by 3. And that's sort of what they point out. Like we start at 2, so it's just a linear function of n, right? So n, and then we just have to figure out, we look at it a little longer, we sort of realize, well, a of 1, it can't be 3 times n because that would be higher than 2. So let's try n minus 1 maybe. N times 3 minus 1 going to be 0. That'll be 2 successfully. So maybe a of n equals 2. And then we move on from there. That's sort of what we did, just less formal, and that's what we got from the slides. I don't exactly know if that's what they were doing, but it's what it seems like. Secondarily, we have what's called backward substitution, which we take our a of n equals a of n minus 1 plus 3. Remember that a of 1 equals 2. And we go, well, we know that a of n is equal to a of n minus 1 plus 3, which means that a of n is equal to a of n minus 1 is actually, well, we know that a of n minus 1 is a of n minus 2 plus 3. And we add the plus 3 on because we're expanding this out to this, right? So we can continue this process. A of n minus 3 is equal to, or a of n minus 2 is equal to a of n minus 3 plus 3. We add our plus 3 for the last one and our new plus 3. And we see that this pattern just keeps going on, right? Until we get to a of n is equal to a of 1 plus, well, we want to specify that we don't want to specify a of 1 because we want to say a of n minus, or minus n minus 1. Why are we specifying that? Because we want to specify that we've iterated all the way down to whatever this was back to our base case, right? Since our base case is 1, it is the starting value minus 1. We'll get a n minus the starting value minus 1 is just equal to 1. But we're specifying that it's n minus 1 because that's the amount of times we've iterated. And the amount of times we've iterated is important because we've added 3 the amount of times that we've iterated. Um, so we've iterated n minus 1 times, so we have to add 3 times n minus 1, because we're adding 3 n minus 1 times. Okay, so now to simplify that down, we can now go a of n is equal to a of 1 plus 3 times n minus 1, and that does eventually get us to our formula quite nicely. I really like that method. It takes a bit to click, but once it has clicked, it's pretty good. So now, let's talk about integer sequences. But before that, a quick commercial break so that I can again blow my nose. That was a difficult commercial break because I was trying to advertise Vim while blowing my nose. Did not work very well. You could use Control Q or colon Q to quit Vim, or colon WQ if you want to save your progress, but your progress isn't good enough to save, or just use the mouse like a loser and click the X. Anyways, summations. I'm pretty excited about summations because they don't very often tell you about summations, and then they're like they explain summations. They just bring it up in a calculus class, and you're like, what do you mean mi equals m k j b you know? It's just terrible. So, what are summations? Well, we use summations to sum sequences from a of m to a of n, or sequences from a of m to a of n, right? So what does that look like? Well, apparently I just cannot, for the life of me, draw one of these summation signs. There we go. So at the top we put m, because it's our max value, and do remember, actually we don't put m at the top, my bad, we put n at the top. N is our max value. And yes, this is inclusive, and we get to pick the index of n. Right now it's just m, because that's our index. So if it starts at 0, that's fine. If it starts at 1, that's fine, because we just get to write it down. And then a of m. So it iterates. So this is equal to a of m plus 1 plus dot 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 plus a of n. So it takes us all the way from here to here and sums them all together. So, what is a useful context for this? Well, I'm glad you asked. Instead of using any of the examples in my slide deck, I'd like to bring you a more down-to-earth example. Let us take a data set. We're going to label our data set we're going to say M, we'll call it capital M, capital S is equal to the sequence 98, 45, 62, 82, 43, 77, 6. A pretty awful range of test scores, but a range of test scores nonetheless. So how many of these are there? 1, 2, 3, 4, 5, 6, 7. And let's say that S of 1 is equal to 98, just for convenience of indexing. So we're going to take our summation, and some of this is probably imaginary math, so I would ignore everything except for the summation stuff. So let's take this summation. What's the max value? It's going to be 7. What's the min value? It's going to be I equals 1 S of I, right? So we're adding all the test scores together, and then we can do this more precisely by saying, instead of putting a 7 up here, which is a fixed value, we can put S and then just write count. I don't know if that's mathematically valid, but we're doing it because no one's going to stop us, and you understand what I mean. So S count, which again is just 7. So what does this do? So it's averaging the test scores. How's it doing that? It's adding them all together and then dividing them by the count. So I'm not going to do the math. You can figure out the math. You just have to understand that this is the average, because in Python this would just be, let's pretend that this is a Python list really quick. It would just be sum of S over len S, right? Like that's all that's happening. But it's pretty cool. So that's all of the actual content, but I've been instructed to make you aware of some formats. I don't know if they'll be on the exam. They probably won't, but we will look at them regardless. So I'm going to quit with the sum format and just start putting sum in a box, and then on the top of the box we'll put n, and at the bottom we'll put k equals 0. AR to the k, where k is not equal to 0. The closed form of that is going to be AR n plus 1 minus a over r minus 1. R not equal to 1. Again, I don't know what these sums are for. I just know that you might want to know them. So I'm giving them to you because, they were in the slides, so it's not like they are a complete waste of your time to look at. I figure worst case scenario, you waste a little bit of time seeing them, never get an exam on them, and never have to worry about it. Oh, no big deal. You learned a little bit, right? Like, nobody honestly cares about your suffering, so stop bringing it up. I think really these are just standard forms that might show up. There's no guarantee that it matters. And up here I put k is not equal to 0. I was lying. It's r is not equal to 0. My bad. Regardless. We're looking at k cubed now. That's going to be n squared, n plus 1 squared over 4. Infinity symbol. That's a rare one. K equals 0. X k times absolute x less than 1. That's not a time, that's a comma. It's just going to be 1 over 1 minus x. Very curious concept right there. Just to double up on that, we're going to go back to our better sum form, because writing sum in a box is just more fun. Don't know if that's just me, but kx k minus 1, comma, absolute x less than 1, 1 over 1 minus x squared. I don't know, something about this is just curious, because infinity, you don't get to go to infinity a lot. Like, it's kind of like a limit, but, those are all the ones. You can look back at this page real quick. Very curious. Good stuff. Have a nice day. Good luck.